This presentation is a part of a lecture series on the C++ programming language by Michael Adams at the University of Victoria in Victoria, Canada. For those of you who might be interested, a copy of the slides for this lecture series can be downloaded from the website whose URL is given at the bottom of this slide. Having looked at the control flow constructs in the language, now we're going to move on to looking at functions. At this point, I need to introduce two terms that relate to functions. And in particular, I need to introduce the terms argument and parameter. So to begin with, an argument, also known as an actual parameter, is a value that's supplied to a function by the caller of the function. So to illustrate this concept by way of an example, if we look at the code down below, here you can see on this line, the code is invoking a function called square, and it's passing it a single value, the value of I. So I is an example of an argument to the function square. The second term I need to introduce is the notion of a parameter. A parameter, also known as a formal parameter, is an object or reference that's declared as part of the function that acquires the value of its corresponding argument upon entry to the function. So to illustrate this concept by way of an example, if we look at the code here for the function square, you can see that this function takes a single value when it's invoked. It needs one particular piece of information, which is the variable I. And this declaration here of the variable I is an example of a parameter. So I will acquire the value of this argument here when the function square is invoked. Basically, I will be passed into this variable I here. And lastly, I should point out that although argument and parameter mean different things, sometimes they're used interchangeably. Strictly speaking, this is an abusive terminology, but because it's done with some amount of frequency, you should be aware of the fact that some people do abuse these terms. Earlier we discussed declarations and definitions in general terms. Now what I'd like to do is revisit this topic specifically in the context of functions. In other words, I'd like to discuss function declarations and function definitions. So a declaration of a function introduces an identifier that names a function and specifies the following properties of the function: the number of parameters that the function takes, the type of each parameter, and the type of the return value of the function. So to give an example of a function declaration, we have a function that's named by the identifier isOdd, and this particular function takes a single parameter, and the parameter has type int, and the return value of the function is type bool. You can also include names for the parameters if you like. For example, we can include a name here x for the parameter which has type int. However, these names are simply ignored by the compiler. They serve no useful purpose inside a declaration. A definition of a function provides all of the information included in a function declaration as well as the code for the body of the function. So an example of a function definition for the isOdd function that we were just looking at above would be what's shown here. So again, we have the identifier which names the function, which is isOdd. The function takes a single parameter of type int, and in this case the parameter has the name x. The return type is bool, and all of this information essentially was captured in the declaration. But in addition, we have the body of the function. We actually have the code that's going to execute when the function is called. So this is what makes this into a definition, is the actual body of the function is included. In C++, there are a number of different ways in which a function can be defined. The first form of a function definition, probably the most commonly used, is the one that's shown at the top of the slide, where first of all we specify the return type for the function. So for example, if the function returns a value of type int, then this return type would be specified as int. This is followed by an identifier which names the function. And then in parentheses we have the declarations of all the parameters for the function, if there are any. And then within brace brackets we have all the statements that constitute the body of the function. An alternative syntax that we can use is referred to as the trailing return type syntax. And in this case, for the return type, instead of giving an explicit type, we use the keyword auto. And this auto serves as a placeholder for the return type, and instead we place the return type at the end here. And it's followed by a minus sign and then a greater than character. Now, a function will execute until a return statement is reached or until the code falls off the end of the function. In other words, it hits the closing brace bracket for the function. And the return statement takes a parameter in the case that the function returns a value. In other words, if the function returns a value, the return statement provides a value to be returned to the caller. And in C++, if a function doesn't return any value, rather than just leaving this return type blank, instead there's a special type in the language called void, which is this type here. And this is what's specified in the case of a function that doesn't return any value. So rather than just not saying anything if the function doesn't return a value, you explicitly say that it doesn't return a value by indicating a return type void. And when parameters are passed to a function, there's two ways in which parameters can be passed. One is by value and one is by reference. When things are passed by value, when the parameters are passed by value, the function is given a copy of the object from the caller, whereas when the parameter is passed by reference, the function is given a reference to the object from the caller. And in order to pass a parameter by reference, we use a reference type for the parameter. And all of these things will be gone through in a little bit more detail in the subsequent slides. So hopefully, if things are not quite clear yet, they soon will be. In C++, it's also possible to use automatic type deduction for the return type of a function. And when this is done, essentially the definition of a function would look something like what's shown here. You would specify auto for the return type, and again, auto serves as a placeholder for the type. Unlike the trailing return type syntax, which would put the return type over here and still explicitly specify the return type, instead you don't specify the return type at all. And what happens is the compiler would look at the return statement inside of the function body, and based on the type that's being returned by the return statement, it would deduce the return type of the function. If the function has no return statement, then the return type of the function would be deduced to be void. And in the case that the function actually does have a return statement that's returning some value, the return type would be deduced to be the type of whatever object is being returned by the return statement. On this slide, we have a few examples of functions. In the first two examples, the function factorial and the function increment, these two functions specify the return type explicitly. So here we're specifying an explicit return type of long for the factorial function, and here we're specifying an explicit return type of void for the increment function. In the next case here, the square function, we're using the trailing return type syntax. So we specify auto, where we would normally specify the return type of the function, and then we specify the actual return type of the function explicitly at the end here. So it's a return type of double. And in the last example here, we're using automatic type deduction in order to deduce the return type. So we specify a return type of auto, and this is not using trailing return type syntax because there is no return type specified explicitly here. So what happens is the compiler looks at the return statement in the function, looks at what's actually being returned, which is x times x, which is a double times another double. And the result of multiplying two doubles is a double, so the result x times x has type double, so the return type of the function will be deduced to be double. Every C++ program must have a function called main, and the reason for this is the main function serves as the entry point to the program. In other words, it's the point from which the program starts executing. The main function has a return type of int, and it can be declared in one of two ways. It can be declared either to take no arguments, like this first declaration here, or to take two arguments, the first of which is an int and the second of which is an array of pointer to char. And in this second case, the reason for allowing these two parameters is to allow some C-style strings to be passed into the program from the environment in which the program is run. And in this case, the parameter argc is a count of how many C-style strings are being provided to the program. And the parameter argument argv is an array of pointers to C-style strings. And typically, although this is operating system dependent, typically argv of 0, in other words, the first element in this array, is a pointer to a C-style string, which is the name of the program that's actually running. Argv of argc, in other words, the one past the end of the array is guaranteed to be a null pointer. And then the remaining values for argv, argv1, argv2, and so on up to argv of argc minus 1 are typically command line options that are specified when the program is run, for example, in a command shell or something like this in the operating system. So these argc and argv parameters provide a means to pass string parameters into your program to control how the program operates. At this point, it's worthwhile to give a simple example illustrating how the two-parameter variant of the main function might work in a particular operating system environment. So suppose in whatever operating system environment you're using, you have some kind of command shell, and you have a C++ program, and the executable file that contains the program is called program, rather unimaginatively. And suppose you're trying to run this program with 3 strings as parameters, so 1, 2, and 3, these 3 strings here. Then the C++ runtime environment would ensure that your main function is called with the first argument, which I've denoted by argc here, being equal to 4, where 4 denotes how many parameters, including the name of the command, are being provided to this program when it's being invoked. So there's 4 of them, basically program, and 1, and 2, and 3. So this is what 4 is corresponding to. And then the second argument, which is denoted by argv here, is an array of pointers to char. And this array would be initialized to contain the strings program 1, 2, and 3, followed by a null pointer. So we have a pointer to the string program, a pointer to the string 1, a pointer to the string 2, a pointer to the string 3, and then a null pointer. As discussed earlier, the main function returns a value of type int, and typically this return value is used to indicate whether the program was successful in performing whatever task it was supposed to perform. And this value is typically passed back to the operating system. Now the program normally terminates when the main function returns. However, sometimes you may want the program to terminate prematurely, in which case this can be accomplished by using the exit function in the standard library. So this function takes a single int parameter, and this int parameter is a value which is passed back to the operating system indicating the reason that the program terminated. So this can be used again in a similar way as the return value for the main function. The return statement in the main function is optional. Even though the main function returns a value of type int, you can actually leave out the return statement in the main function. And if you do this, the main function will behave as if it executed a statement return 0. In other words, if you fall off the end of the main function without actually returning any value by executing a return statement, the value 0 will be returned. At this point, I need to introduce the notion of the lifetime of a variable or object. And the lifetime of an object is simply the period of time in which the object exists. So there's various different possibilities for the lifetime of the object. It might be just the block in which it's defined, or it could be the function in which it's defined, or it could be a global variable, in which case its lifetime is the entire duration of the program. So in the code example that's given on this slide, we have a global variable x of type int, so its lifetime would be the entire duration of the program. And then we have a function here, waste time. It has a local variable called j, which is of type int. The lifetime of this variable would be from the line of code that defines it until the end of the block in which it's defined. In other words, the end, in this case, the end of the waste time function. The integer variable I in this case, the lifetime of this variable would just be the duration of the for loop. If you remember, if you define a variable in this initializer for the for loop, the lifetime of any of these variables is just the lifetime of the actual for loop itself. When a function call takes place, each parameter of the called function must be initialized from the corresponding argument provided by the calling function. And there's 2 ways that this initialization can be accomplished. One is by using pass by value, and one is by using pass by reference. In the case of pass by value, a new object is created that's local to the called function, and the value of the argument from the calling function is propagated into this new object, for example, by copying its value. In the case of pass by reference, the called function is given a reference to the object from the caller. And in order to achieve pass by reference, the function parameter that is declared to have a reference type, whereas for pass by value, the function parameter is declared to have a non-reference type. And there's two main reasons for using call by reference. One is that sometimes the particular argument that's being passed into a function would be very expensive to copy. Therefore, in order to make things more efficient, a reference is used, because a reference is just a nickname or alias for an already existing variable. So when a reference is used, no copying is required, because essentially you're just referencing some variable that already exists in the code. The other reason for using call by reference is sometimes a function may want to change the value of the object in the caller. And this can only be achieved if a reference is used. Otherwise, the function would simply be changing a local copy of some parameter that was passed into it from the calling function. To illustrate the difference between pass by value and pass by reference, it's worthwhile to consider an example. So in the code that's shown on this slide, I have two functions that perform an incrementing operation. In the body of the function, they're incrementing some variable. The first one's called increment 0, and the second one's called increment. And the only difference between these functions, if you look carefully at them, the first version of these two functions, the one called increment 0, it's passing by value, because the function parameter that's specified here is of type int. It's not a reference type. There's no ampersand or double ampersand after the int, so this is not a reference type. So this is going to be using pass by value. In the case of this function, we have an ampersand after the int, which means that this is the type of this variable x is a reference to int. So this is using pass by reference, because we're using a reference type for the parameter x. Now what I would like to do is I'd like to consider some code, this code called func, which is going to call the increment 0 function, and it also calls the increment function. So we create an integer variable I, we initialize it to 0, and then we call the increment 0 function to perform an increment operation. What's important to observe here is that when this function call is made, it will not result in I being incremented. In other words, after this function returns I on this line here, which is just a comment, if we were to print the value of I on this line, it would still be equal to 0. In other words, this function will not increment the value of I. On the other hand, this function call that we make here, when we call the increment function, and we pass it the argument I, this will have the effect of incrementing the variable I. And if we print out the value of I on the line below here, it will print the value of 1, because I will have been incremented. Now what's important to understand is why is it that we have these two different behaviors with the function increment 0 and increment 1, where one of them actually does have perform the incrementing operation as we expect, and one of them doesn't. And this relates to pass by value versus pass by reference. So in the next few slides, I'm going to explain in more detail why it is that this sort of behavior results. To begin with, let's consider the case of the increment 0 function, in other words, the one that's using pass by value. So if we look at the code here, we have our function increment 0. It takes a single parameter x, which is of type int, and because int is not a reference type, in other words, it's not int ampersand or int double ampersand, it's not a reference type, so this is going to use pass by value. Now let's look at the function that's calling increment 0. We have this function func. So the first thing this function does is it creates a new integer variable, int variable, called I, and initializes it to 0. So in terms of the picture in memory, for this function, we're going to create a new integer variable I, which allocates some chunk of memory, and then it puts the value 0 into this chunk of memory that's representing I. Then we proceed to call the function increment 0, and we're passing it I as an argument to the function. Because we're using pass by value, what happens is when this function increment 0 is called, a new local variable for this function is created called x. So it creates a new local variable called x. So we create some chunk of memory to hold this variable x. And then what pass by value does is it propagates the value of this variable here, the variable which corresponds to the argument in the caller. It propagates this value into the new variable that's created. And this propagation is done by copying in this case. So the value 0 here is copied into this new variable. Then inside the increment 0 function, when we say plus plus x, in other words, when we're incrementing x, the variable that we're incrementing is this local copy of this variable here. In other words, we're incrementing this variable x, so this variable will be incremented from 0 to 1. So x will then have the value of 1 stored in it. And then the function increment 0 returns. And when increment 0 returns, this local variable x is destroyed, so it goes away. And then all we're left with after we returned is this variable I, which is still equal to 0, because it was never changed by the increment function. So this is the reason why when we pass by value in this particular example, the value of I remains unchanged after the function increment 0 returns. Now let's look at the case of pass by reference. So in this case, we're referring to the function that was called increment. And the increment function, it had a single parameter which was of type int ampersand. In other words, it's a reference to an integer, or more specifically an L-value reference to an integer. But the important thing is it's a reference type. Because of this, pass by reference will be used by this function. So now let's go and look at the code which calls the increment function, the function func, and look in more detail what happens when this particular function func is executing. So the first thing that func does is it creates a new variable called I of type int and initializes it to 0. So when this line of code executes, what's going to happen is some chunk of memory will be allocated to hold the variable I, and then the value of 0 will be written into this variable. So we have a picture that looks like this in memory. Then on the next line, we proceed to call the increment function, and we pass as an argument to this function I, which is this variable here. But this is passed by reference. So when the function increment is called, x is a reference. In other words, it's a nickname or alias for some already existing variable. So when the increment function is called, there is no new local variable that's created for this function. Instead, x is just a nickname for this variable I. So inside the function increment, whenever we refer to the variable x, we're just referring to the variable I, because x is a nickname for I, or alias for I. So then inside this function, when we say plus plus x to increment x, because x is a nickname for I, when we say plus plus x, this is the same as saying plus plus I, because x and I are the same variable. One is a nickname for the other. So when we say plus plus x, it's going to actually increment this variable here, I, which will change this value of 0 to 1. Then after we've incremented x, this function returns. And when the function returns, the variable I after this function call returns, I will have the value 1, because this value is actually incremented by the function increment. Earlier when we were discussing types, we talked about the const qualifier. And what I'd like to do is I'd like to revisit the const qualifier in the context of pass by reference, just to help illustrate how things can go wrong in terms of the const qualifier and using it correctly. And in this particular example, what we have is a function called average. It takes in as a parameter a real vector, or a reference to a real vector, because we have an ampersand here. What real vector actually is in full detail is really unimportant. The only thing that's important to understand is just conceptually it happens to represent a vector of real numbers. So the point of the average function is to compute the average value in this vector. So we're passing in some vector x, and we want to compute the average value of all the elements in the vector. So in the code for this function, we create a double variable a to hold the average result that we're about to compute. Then we have some code here represented by this comment. I'm not actually showing what the code looks like because it's not really relevant from the point of view of this particular example, but the code represented by this comment is the code that actually computes the average and stores it into the variable a. And then at the end, we return the average value a that was computed by this function. Now, if we look at the code up above that's using the average function, we have this function called func, and you can see it's calling the average function here. So what we're doing in this function func is we're creating a double variable a, which is going to hold the average value that we're about to compute. Then we call some function getVector, which returns a real vector as a return value, and then we assign the returned value to this real vector v. And then we call the average function, passing as a parameter to this function v to compute the average of this vector v, and then we store the return value into A, the average that's computed. Now this code may look perfectly okay, but it has a very serious problem associated with it. And the problem is that the const qualifier is not being used correctly in this code. In fact, there is no const qualifier here, and this is actually the problem. And the issue here is if we look at this average function in more detail, really the problem here lies in this average function. The average function, it's receiving this parameter x by reference. And when we have a reference, since the reference is not a reference to something as const, there is no const in front of real vectors. So this reference is a reference to something that we're allowed to change. I'll say this again because it's important. It's a reference to something that we're allowed to change, with emphasis on the words that we're allowed to change this value. And the problem here is that conceptually this doesn't really make sense, because as far as this function is concerned, we're allowed to change the value of x. But if you think about things logically, if we're computing the average value of the elements in this vector, it would make no sense logically for the process of computing the average value of the vector x to actually change the value of x. It would be kind of ridiculous if computing the average value of this vector actually changed the values that were stored in the vector. However, because we haven't specified this reference as a reference to something that's const, in other words, it's not a const real vector reference, it's just a real vector reference. Because of this, we're allowed to change x inside this function. And this causes problems, as I'll explain on the next slide. So this code, although it will compile as shown on this slide, it's wrong. And in some circumstances, this code will actually fail to compile. So on this slide, we have exactly the same example as on the previous slide. The only difference is I've just made one small modification to the code. And the modification I've made is I've added the keyword const in front of real vector here. And this would not be an unreasonable thing to do. All I'm saying is that when we call the function getVector and it returns some vector and then we store that vector into v, we're never going to change v anywhere else in this code, so why not make it constant? Why not put a const in front of the real vector to say that we're not ever going to change v once it's been initialized? This is a perfectly reasonable thing to do, and there's absolutely nothing wrong with doing this. But as soon as you do this, this code will fail to compile. And the reason why is because of the problem that's really lying in the average function here. And the reason why this code will fail to compile is because this reference here, the parameter x for the function average, this particular parameter here, its type is real vector ampersand. In other words, it's a reference to a real vector. It's a reference to something that we're allowed to change. And this is where the problems begin, because if we call the function up above here, the function average, and we pass it v, what's the type of v in this case? Well, v is a constant real vector. It's a real vector that cannot be changed. It's const. So v is not allowed to be changed. Now let's see what happens if we actually try to call this function average. In other words, if the compiler let us do this, what would this imply? Well, when we call the function average, we're passing by reference because we have this ampersand here. So x is an alias or nickname for v. In other words, x and v are the same variable because one is an alias for the other. But this is where the problems arise, because notice that x is a reference to something we're allowed to change. In other words, x is a reference to a real vector, not a reference to a constant real vector. Therefore, it's perfectly legitimate for us to change the value of x because there's nothing preventing us from changing its value because it's not a reference to something that's const. However, consider what happens if we change x. If we change x, x is an alias or nickname for v. So if we change x, which we're allowed to do, we change v. But v is const because v was declared to be const. So v can't be changed. And the compiler is smart. It sees this. It sees the fact that we're passing as a parameter to average something that can't be changed, and yet the function average is not making the promise that it won't change this thing that's being passed into the function. Therefore, the compiler will generate an error saying, no, you can't do this. And the reason why, essentially, is that the function average has a problem with it, a conceptual problem, which is that because this function, it does not logically make sense that it should change the value of the vector that it's computing the average of. In other words, it makes no logical sense that x should be changed by this function. Because of this, the function should make the promise that it doesn't change x. In other words, the real problem in this code is there should be a const right here in front of real vectors. So the type of x should be a constant reference to a real vector. And if we put the const keyword in here, then everything will be fine, the code is correct, and it will work as we would expect in all cases. And the general rule of thumb here is anytime that you're using references, or the same idea applies to pointers as well, any type that's used to refer to something else, you have to make sure that if that thing that refers to something else is not ever going to be used to change that something else, you have to make it const. Otherwise you run into problems like this. Normally when a function is called, control must be transferred from the calling function to the called function and back again. This process of transferring control has overhead, however, and although in many cases the cost of this overhead is negligible, sometimes this cost can become quite significant. And in particular, when a function is called that is extremely short, the time required to transfer control to and from the function can become very large compared to the time actually spent performing computation inside the function. And in such situations, an optimization known as function inlining is very beneficial. And basically what function inlining does is the following. When a function is inlined, each place in the code where the function is called is replaced by the code of the function itself. And in this way, the overhead of transferring control from the caller to the callee and back again is eliminated. And due to the importance of the function inlining optimization, we may wish to have a way to hint to the compiler that it would be beneficial to inline a particular function in our code. And for this purpose, the C++ programming language provides the inline qualifier for functions. So if we look at the code example at the bottom of this slide, we have just a very simple function. It's being passed an int called x, and it's checking to see whether x is even or not, and it's returning true or false based on whether x is an even integer. And you'll notice that in the definition of this function, we've added this keyword inline. And this keyword is basically a hint to the compiler saying it would probably be very beneficial to inline this function. And one last comment about inlining. When a function is defined to be, or when a function is inline, its definition must be visible at the point where the function is being called. And this makes sense if you stop to think about it. In other words, if you're going to use a function and it's an inline function, the compiler needs to know what the definition of that function is so that it can essentially paste the code for that function into the place where you're calling it. So this is an important thing to keep in mind when you're using inline functions, is that the function definition has to be visible at the point of using the function. On this slide, we have an example to better illustrate function inlining. So in this case, we have a function called isEven, which takes a single int parameter, x, and essentially what it's doing is it's checking to see if x is an even integer or not, and it returns true or false, a bool, depending on whether or not the result, or the integer x, is even. And as you can see, the code for this function is very, very short. And we've made this function an inline function by including this keyword inline here. So this is a hint to the compiler that we'd really like this particular function to be inlined. Then I have this function called myFunction, which is calling the function isEven, this function that we've requested be inlined. And if the compiler respects our wishes and actually does inline the function isEven, this code here on the top part of the slide would be transformed into the code on the bottom part of the slide. And in this transform code here, notice that there is no function call anymore. The code that actually does the computation to test if the integer is even, in other words, the code that corresponds to this code here, has actually been folded into the myFunction function itself. So the function call has been eliminated, therefore the overhead of the function call has also been eliminated. And for such a short function like what we have with the isEven function here, because it's performing such a simple computation, this inline code is probably going to be much more efficient than the non-inline version would be. Earlier in the context of variables, we talked about the Constexpr qualifier. The Constexpr qualifier can also be applied to functions. The general idea is the same. Again, Constexpr is used to indicate that something is a compile time constant. It can be determined at compile time. And if we apply the Constexpr qualifier to a function, essentially what that indicates is the return value of the function is a constant expression, provided that all of the arguments that are provided to the function are also constant expressions. And this proviso is important. This is only true if all of the arguments that are provided to the function are constant expressions. So another way of looking at this is if all the inputs to the function are things that are known as at compile time, in other words, all the input parameters, then the return value is also known at compile time. And Constexpr functions are implicitly inline, and they're also quite restricted in what they can do. For example, a Constexpr function can only call other functions that are Constexpr functions. And I have a code example here. So suppose that we want to have a factorial function that can compute the factorial of some int value, n. And we want to be able to use this factorial function in ways that would only be allowed if the result of the factorial function was a constant expression. So we declare this function to be a Constexpr function, so we include this Constexpr keyword here. And this is actually a recursive implementation of factorial, because you can see factorial actually calls itself recursively. So it's implementing the factorial computation in a recursive manner. Now, if we try to use this factorial function, suppose that we want to create an array of ints called u, and we want to specify the size of the array, but we want to specify the size of the array using the factorial function, because we want the size of the array to be 5 factorial. If this function wasn't declared to be Constexpr, this line of code here would fail to compile, because in C++, the size of an array must be a compile time constant. In other words, it must be a constant expression. In this case, this will not generate a compile error. It's fine because the factorial function is being passed arguments that are all constant expressions. 5 is a constant expression. 5, the value of 5 is known at compile time. Therefore, all of the input parameters to the function are compile time constants, or constant expressions. Therefore, the return value is also a constant expression. Therefore, factorial of 5 is a constant expression. So this line of code is fine, it will compile. However, this line of code down here will fail to compile. Here, again, we're using the factorial function. But in this case, the argument that we're providing to the factorial function x is not a constant expression, because on the line above you can see it's just a regular variable. Because x is not a constant expression, the return value of factorial is not a constant expression. Therefore, we're trying to plug a non-constant expression in for the size of an array, and this is not allowed by the language. So this line of code here would generate a compiler error. On this slide, we have a code example that has a Constexpr function, in particular the function power_int. So what this function power_int does is it has two parameters, as you can see, a parameter x, which is a double, a parameter n, which is an int, and it computes x to the power n, where n can be positive or negative. And we just have the code that you would expect here. It computes the power by just doing repeated multiplication. Then down below in the main function, we have some code that actually uses the powerInt function. So the first function call here, when we invoke powerInt on this line, notice that both of the arguments to the function are constant expressions. 0.5 and 8 are constant expressions. This, however, in and of itself does not guarantee that the compiler will compute the result of this powerInt function at compile time. The reason why is compilers are lazy. They don't really want to have to do any more work than they have to. So unless you really force it to compute something at compile time, the compiler may be kind of resistant to doing so. In this particular case, however, because we assigned the result of this function call to a Constexpr variable, this will force the compiler to have to evaluate the function at compile time. The reason why is because the variable a is a Constexpr variable. This means that a must be computed at compile time. But to compute a at compile time, the compiler is forced to call the function powerInt at compile time, because otherwise it doesn't know what value should be assigned to a. So on this line here that we're looking at, powerInt is absolutely guaranteed to be computed at compile time. If we just change this line slightly and drop the Constexpr, which is in effect what we have on this line down below, line 19, so here b is not a Constexpr variable. In this case, even though powerInt is being invoked for arguments that are both constant expressions, 0.5 and 8 are constant expressions. So in principle, the compiler could evaluate the result of powerInt at compile time, but it's not required to do so, because the result of this function is being assigned to just a regular non-Constexpr variable, so there's no guarantee that b has to be computed at compile time. So in the case of this line here, powerInt may or may not be evaluated at compile time. You can't really say for certain. If you really wanted it to be computed at compile time, you could force this by putting Constexpr in front of double here. In other words, force b to be a Constexpr variable. And then the last place where power int is called in the main function is this line here, where we're invoking power int with the arguments x and 2. Now clearly x is not a constant expression, therefore the arguments of power int are not all constant expressions here, therefore the compiler cannot evaluate power int at compile time in this case. So this evaluation of power int is absolutely guaranteed to take place at runtime. As we've seen, C++ has both Constexpr variables and Constexpr functions. And essentially, Constexpr provides a mechanism for moving computation from runtime to compile time. So why might we want to do this? Why might we want to move computation from runtime to compile time? Well, there are a number of advantages in doing this. Perhaps the first and most obvious one is that there's no execution time cost at runtime for computations that are performed at compile time. So in other words, when our program first starts running, any of the computations that were done at compile time, since they don't need to be done when the program's running, it costs you 0 CPU instructions to compute those values because they're pre-computed for you when the program starts running. We can reduce the size of our code potentially as well by using compile time computation. The reason for this is if something is computed at compile time and it doesn't also need to be computed at runtime, then the CPU instructions that do that computation don't need to be included in the executable program because it doesn't actually need to be computed when the program's running. So this can reduce the size of the program. Another advantage to using compile time computation is that it forces certain types of errors to be found earlier. Often you can find errors at compile time or link time rather than finding them at runtime by forcing the computation to be done at compile time. And again, it's advantageous to find errors sooner rather than later. So in other words, it's preferable to find errors at compile time rather than finding errors in the program at runtime. And then lastly, if you're using multi-threaded programs, then there can be an advantage in terms of compile time computation doesn't require any synchronization, whereas runtime computation may potentially need some synchronization. So this eliminates one headache when doing multi-threaded programming. And then one other comment I should make with respect to compile time computation versus runtime computation is that when floating point arithmetic is involved, compile time and runtime computations may not produce exactly the same results. And this is due to differences in such things as the rounding mode that's in effect. In other words, the rounding mode that the processor is using, like round towards negative infinity, round towards positive infinity, rounds towards nearest, for example. It could be different when you're doing the computation at compile time versus runtime. So you could produce slightly different or maybe significantly different results depending on the effects of rounding. Another potential reason for having differences between compile time and runtime computation is if you're using a cross compiler. In other words, if the CPU architecture that you're compiling on and the CPU architecture for which you're producing code are different. Like for example, in embedded applications, often you're not running the compiler on the same architecture that you're going to be running your final code on. And in this case, because it's a different processor that's executing code at compile time from the processor that's running the code at runtime, it would be unreasonable to expect that they're going to produce identical results. And typically, they probably won't be quite the same. This is not necessarily a big problem, but something to be aware of, just in case you might care that the results are exactly the same. The C++ programming language supports something known as function overloading. So what exactly is function overloading? Well, function overloading is a feature of a programming language that permits the definition of multiple functions with the same name. So as a matter of terminology, a function is said to be overloaded if it's named by the same identifier as one or more other functions. And when a call is made to an overloaded function, the decision of which particular function to invoke is made based on the number and types of the arguments that appear in the function call. The concept of function overloading is probably best illustrated by an example. So on this side, we have an example utilizing function overloading. And in this particular code example, the print function is overloaded. There are two different functions that are both identified or named by the identifier print. So here we have the identifier print naming this function, and also the identifier print is used to name this function as well. So the print function is overloaded. The first overloaded version of the print function takes a single parameter of type int, and the second overloaded version of the print function takes a single parameter of type double. And clearly these functions are different functions. They have different code in their body, as you can see from the two definitions here. Now in the code below, we have a function called demo, which is going to call the function print a number of times here. And what we want to look at is which of these overloaded versions of print is going to be called in each case. So in this demo function, we create an int variable called I and initialize it to some value. We create a double variable called d and initialize it to some value. And in this first function call that's made to the print function, the argument that's being passed in the function call operator is I. And I has type int. As you can see from above, I has type int. So what happens is the compiler will look at the two overloaded versions of print here. We have print, the first one, which takes a single parameter of type int, and then the second overloaded version of print takes a single parameter of type double. So if it's trying to choose between a parameter of type int and a parameter of type double, because the actual argument that's being passed has type int, the first of these two functions is a better match. It matches more closely the type of the argument that's being passed. So in this case, this function would be called in order to correspond to this function call operator here. So this will call the function print, which takes a single int parameter. If we move on to the second function call that's invoking the print function, in this particular case, we're passing a single argument which has type double, because if you look up above, d has type double, so this has type double, this argument. And then again, we have two choices of the function that can be called. One which takes a single parameter of type int, one which takes a single parameter of type double. Well, the one that takes a parameter of type double is a better match to this argument d, because this argument d has type double. So this particular function call would call the function print that takes a parameter of type double. And it works similarly for the remaining examples here. If you bear in mind that 42 is an integer literal of type int, and that 3.14 is a floating point literal of type double. In C++, it's possible to specify default values for arguments to functions. And this is probably best illustrated by way of an example. So let's consider a logarithm function. We want to compute the logarithm of x with base b. So we have a double parameter x and a double parameter b, and our return value is a double, which is the result of the logarithm computation. And of course, there's a standard formula that we can use here to compute the logarithm of x with base b, which is the formula that we're using here. Then down below, we have a declaration of this function. And what's special about this declaration is notice this equal 10.0 here. This is a default argument. So what this is saying is if we call the logarithm function and we don't provide a second parameter, treat the second parameter as if we specified it to be 10.0. So this is a default value for the second argument to this function. So in this function below, demo, where we're going to use the logarithm function, suppose that we call the logarithm function this way. So we say logarithm and we pass only a single parameter, 100.0. This is the same as calling logarithm with 100.0 for the first parameter and 10.0 for the second parameter. This 10.0 is coming from this default value here. Because we didn't specify, over here, we didn't specify the second argument for this function, it defaults to this value that was provided as a default value. On the other hand, if we call the logarithm function, we provide two parameters, or two arguments to this function. In this case, this will just do the straightforward thing you would expect. It would invoke logarithm with the first parameter being equal to 4.0 and the second one being equal to 2.0. So the default value here will only be used in the case that we don't actually provide the second parameter. If we do provide the second parameter, it will use the value we specified explicitly. Since functions can be overloaded, a well-defined set of rules is needed in order to determine which overloaded version of a function should be invoked by a given function call. When an overloaded function appears in a function call, the function that will be invoked is the one with the best match for the arguments provided to the function call. The process of determining this best match considers all functions in scope that could possibly be called and proceeds in the following manner. First, for each argument provided in the function call, find the set of functions that best match that argument. And in order to determine the best match for each argument, the matches are attempted in the order listed on the slide. So the best match is an exact match. So for example, if the argument that's used in the function call has the same type as the parameter that appears in the function declaration or definition, then we have an exact match, and this is the best type of match. Also, trivial conversions are allowed as well. So for example, if the type of the argument is type t, where t might represent int, for example, or char, and the actual parameter in the function is tref, in other words, a reference to type t. This is considered a trivial conversion, and it's essentially as good as an exact match. And there's various other trivial conversions. You can also add const or add volatile. These are also trivial types of conversions. The next type, or next best type of match is a match with promotions. This is where you're changing some numeric type, for example, into a larger type. So converting an int to a long or a float to a double and so on. The next best match is a match with standard conversions, which would be converting something like float to int or double to int and so on. And then the next best match is a match with user-defined conversions. And then the worst kind of match is a match with an ellipsis. And after the set of best matches for each argument has been determined, the best match is computed as the intersection of these sets. And if the set of best matches contains exactly one element, this element is chosen as the function to call. On the other hand, if the set of best matches is either empty or contains more than one element, the function call is invalid, because essentially what this means is either no matches were found, there is no function to call at all, or multiple equally good matches were found. And this is also deemed to be an error as well. If there's more than one function that is an equally good match to be called, rather than the compiler randomly choosing one, it will just say, I don't know what to do, and generate a compile error, and then the programmer has to fix this and modify the code so that it avoids this ambiguity where you have multiple equally good matches. And admittedly, argument matching in its full detail is somewhat tricky, but practically speaking, a very basic understanding is often sufficient for at least beginning programming and a reasonable amount of programming. In any case, this process of determining a best match will probably be made much easier by way of an example, which is coming next. On this slide, we're going to look at an example of argument matching to help illustrate how this process works. So in this example, we have two overloaded versions of the max function. The first one here, which takes two int parameters, and then the second one here, which takes two double parameters. And in the code below, we have three function calls which are trying to invoke a function called max. This function call here, this one here, and then this one here. And in each case, we want to figure out which of these two functions, these overloaded functions here, are going to be called in each case. So we have three variables, I, j, k, that are of type int, and then three variables, a, b, c, which are of type double, which are going to be used in the code below. So let's look at each of the function calls which are trying to invoke a function called max. In the first case, in this case here, we have two arguments that are being passed, and they're both of type int, because if you look at the type of I and the type of j up above, they were both defined to be of type int. So both of these arguments are of type int. So the way argument matching works, we do a match on each argument individually. So we look at the first argument, the type of the first argument is int, and then for each of these overloaded functions here, we look at the type of the first parameter for the function. So this one has type int, this one has type double. Int is a better match than double because int is an exact match. So in this case, the better match for the first argument is going to be max int int, the one that has int for the first parameter of the function. Then we go on to the second argument, which is being passed in this function call, which is j. And again, j, if you look up above, it's of type int. So j has type int. Then we look at the two overloads of the function max. The first one has int for its second parameter, and then the second overload of the function max has double for its second parameter. And of these two types, int and double, int is a better match for j because j has type int. In other words, int is an exact match for the argument j that's being passed. So the best match on the second argument is max int int again. So in other words, the version of max that takes two int parameters. And then to find the best match, what we do is we take the intersection of these two sets, the intersection of the set for the first argument and the set for the second argument. Each of these sets only has one element in it in this case, and they're both the same. So when we take the intersection, we get max int int again. Therefore, for this particular function call here, the function that will be called will be the function max int int. In other words, the function that takes two integer parameters. Then if we move on to this next function call, to the function named max, in this particular case, we have two arguments, a and b, and in this case, both of these arguments are of type double. If you look up above, a and b were defined to have type double. So now we, again, look at each of the arguments individually. So first we focus on the first argument here, which is a, and a has type double. So then we look at the two overloads of this function, max, and concentrating on the parameter type for the first parameter of the function. In the first function it's type int, in the second function it's type double. But because a has type double here, the better match is the second function here, the one that has type double for its first parameter. So in this case, max double double is going to be the one that's the best match for the first argument. So it's this function here. Then we move on to the second argument in the function call, which is the argument b. b has type double. If you look up above, it's defined to have type double. So then we look at the two overloaded versions of max here, focusing on the type of the second parameter. In this case, it's type int. In this case, it's type double. But double is a better match because the type of b is actually double. So this one is an exact match where int would require some type of conversion or promotion. So in this case, for the second argument, the better match is the function max double double again. And if we take, to get the best match, what we do is we take the intersection of these two sets. And both of these sets have a single element and it's the same element. So when we take the intersection, we just get max double double again. And this best match here is going to be the function that's called. So it will call the function max double double. In other words, the version of max which takes two double parameters. Then we move on to the last function call here, invoking max. And in this case, we have two arguments. I, which is of type int, because if you look up above, I has type int. And then b, which is of type double. If you look up above, b has type double. So again, we go through the similar process. First, we'll focus on the best match for the first argument. So in this case, the first argument has type int. So we go and look at these two overloaded versions of max. The first one has int for its first parameter. The second overload has double for its first parameter. But int is a better match than double for the first parameter because the first parameter actually has type int. So if we choose this first overload here, we have an exact match of this type int with the type of I here. So the best match for the first argument is going to be max int int. Then if we go on to the second argument, b has type double if you look up above in the code. So then we go and look at these two overloads of max and we focus on the type of the second parameter. In the first case, the type is int. In the second case, the type is double. But of these two types, int and double, the one that's a better match for b is double because b actually has type double itself. And so the type double would be an exact match for b. So of these two overloads here, the one that we want to choose is the one max double double for the second argument. And then to find the best match overall, which is the function that's going to be called, we take the intersection of these two sets. But you'll notice that these two sets have no overlap. So when we take the intersection, we get an empty set. And if you recall, if the best match has either no elements or more than one element, then you have an invalid function call. And in this particular case, we have, because the set is empty, we have an invalid function call, and more specifically it's an ambiguous function call because it turns out there's more than one function that could actually be called here, but the problem is none of them is clearly better than the others. So the function call is ambiguous, and the solution to this problem, well, there's various ways it can be solved, but for example, this I could be cast to a different type in order to avoid the ambiguous function call, or b could be cast to another type, for example, to solve this problem. When writing code, it's highly advisable to include a number of self-checks throughout the code in order to ensure that the code is behaving as expected. And this is very helpful for checking for bugs and helping to isolate them when they occur. So there are two times at which you might want to perform checks in the code. One is at compile time and one is at runtime. For the purpose of doing runtime checks, the assert macro is provided by the standard library. So the assert macro is defined in the header file cassert. So if you want to use this macro, you have to be careful to include the header file cassert. And the macro takes a single argument, which is a Boolean expression. And the basic idea is the Boolean expression that you're providing to the macro is a condition that if your code is behaving reasonably sanely, should always be true. So if the Boolean expression evaluates a false, this would be an indication that something is seriously wrong with the code. And probably the execution of the program should be terminated because something is really, really wrong with it. So if the condition that's provided to assert fails, in other words, it fails to be true, it's false, the program will be terminated by calling the abort function. And as an additional benefit to using assert is that if the ndebug preprocessor symbol is defined, in other words, you do hash define ndebug, then all assertions in your code will effectively be commented out. So this is very useful in practice, because often when you're testing things before you ship the software to the customer, you want to have lots of code for doing self-checks to help detect bugs if there are any there. But some of these tests may be quite expensive to do in terms of computation time, so you probably don't want to leave them in the final product that ships to the customer. But it would be nice if you didn't have to go through the whole code and delete all the lines that had these checks on them. In other words, go through and delete all the lines that had the assert macro being used on them. And in fact, you don't need to do this. All you need to do is just define the ndebug preprocessor symbol and then recompile. And when you do this, all the asserts will effectively be commented out in your code, and they don't cost you anything therefore. And just to give an example of how you might use the assert macro, here I've included the cassert header file, because in order to use the macro, you need to include this header file. And I have this function called square root, which is just intended to compute a square root of a real number. And the number is represented by a double, so we're passing in a parameter x for which we want to compute the square root. Its type is double. And obviously it doesn't make sense to compute the square root of a negative number. So maybe in our code we want to have an assertion saying the value that we're computing the square root of x is strictly greater or equal to 0 and can't be negative. And then in this way, if someone did try to call our code in a ridiculous manner, passing in a negative number, rather than the code going and doing some kind of weird things, the program would abruptly terminate its execution, printing out a message that this assertion had failed, and then we know that someone's trying to take the square root of a negative number, and we can try to track down that particular bug.